All right. Welcome to the Blue Economy CRC webinar series for 2026. I'm Dr. Yunil Chu, Research Fellow at the University of Queensland. Firstly, on behalf of the Blue Economy CRC, I'd like to begin by acknowledging the traditional custodians of the various lands on which we work today and the Aboriginal and Torres Strait Islander people participating in this webinar. I pay my respect to elders past, present. With a 10 years life, the Blue Economy CRC has assembled 46 past and present industry, government, and research partners from 10 countries with deep expertise in aquaculture, marine renewable energy, maritime engineering, environment assessment, and policy and regulation. We currently work with 41 active participants from across 9 countries, supported by a network of strategic partners. Through targeted and industry-focused research and training, the Blue Economy CRC drive innovative, commercially viable, sustainable offshore development and the new capability that significantly boost renewable energy output, seafood production, and job creation. We are transforming how Australia ocean industry operate and grow. Our purpose underpins the growth of our partners in the blue economy through increased offshore renewable energy and sustainable seafood production. Our vision is a sustainable blue economy underpinned by our innovative industry and trusted stewardship of our oceans. Our values are innovative and industry focused, have integrity, and are responsive to our partners' needs, are collaborative, and aim for excellence as well as supportive. Today's webinar will present the findings of Phase 2 of the SeaFisher, a novel offshore fish pen system designed to enable reliable and scalable aquaculture operations in exposed offshore environment. A Q&A session will follow after all 5 presentations, which I will facilitate. So please place your questions in the Q&A box at the bottom of your screens. You can also upvote any questions that you wish to be answered so that the popular votes get prioritized to the top of the list. Our presenters can also respond to your questions through text throughout this webinar and leave a few questions to answer live at the very end. Now, without further ado, I will start with our first presentation on physical model testing of novel submersible offshore aquaculture structure, presented by Dr. Eric Gubesh from AMC Utah. Eric?
Thank you, Yuno, for introducing me and for the introduction this morning. Let me just share my screen. Okay, you guys should be able to see the full screen up there. Is that right? Very good. Okay, my name is Eric Gubesh, and I'm a hydrodynamics researcher at the Australian Maritime College at the University of Tasmania. And over the last year and a half, I've spent quite a bit of time working on the aquaculture offshore structure that the blue economy has developed, which is known as the SeaFisher. Now, there's been a lot of discussion and conversation about translating the inshore aquaculture industry that we have in Tasmania into more exposed waters. However, there's a lot of challenges that actually come across from lots of different aspects when you start moving into high energy sites. Of course, you have concerns about fish and environmental health, there's operational logistics issues, and there's a whole lot of regulatory problems that we need to overcome as well. But fundamentally, if the structure itself doesn't survive the extreme waves or the conditions out there at sea, the system needs quite a lot of work to improve. So on my screen here, I've got different examples of aquaculture structures that were formerly inshore models that were actually moved into the open ocean. Now, I need to say that none of these are actually from Tasmania. I believe these are all scattered from around the world, and nearly all of them have suffered catastrophic failures. So what's the solution? A potential way of fixing this problem is simply to submerge the fish pen itself below the surface of the waves when a high energy event like a storm comes along. This concept makes a lot of sense when you think about it from an objective point of view, because most of the energy is actually concentrated at the surface where the waves may be breaking or where there's very large dynamic motions. And by putting it further down, what you're doing is dissipating the energy. So the research that I'm actually looking at is how much difference does it actually make? Now, the SeaFisher model that we are talking about here is a very large offshore structure. The pen spacing is 120 meters in length, it's 40 meters wide, and the pens are 20 meters in depth. That means that this structure can accommodate about 300,000 5-kilo fish. And the model itself, or the structure itself, is designed so that it can be submerged about 30 meters below the designed water line. It has a single point mooring, and what that means is the whole system can yaw and move to align with what the environmental forces are doing. And the entire structure is actually made out of HDPE, similar to the plastics and materials that the inshore aquaculture actually use. So how do you actually model something like this at a 1 to 50 scale? The first thing you need to do is you need to start looking at what are the flow and the force regimes that are actually acting on the model. Now, the model itself, I used the Froude's scaling laws, and what it meant is we ended up with a physical structure that was as appropriately geometrically scaled to the full scale. This includes everything from water depth to the waves to the physical structure. Overall, the model itself is about 2.4 meters long. It's made completely from carbon fiber and 3D printed plastic joiners. All of those plastic joiners were waterproof with epoxy so that the entire thing can be submerged and then resurfaced back up as per the actual intended design. It was ballasted very carefully with a series of different lead weights so that we could actually control the center of gravity. And everything was done to the highest level of precision that we could actually make in the labs here at AMC. So we ended up with a very good model. Now, the wireframe itself, I think, is a very good representation of the model. On the other hand, the netting that goes around the outside is probably the most challenging part of this physical experiment that we actually completed. So the image that we can see on the left, this is the actual Kiko net from the manufacturer. It has a solidity ratio of somewhere between 0.16 to 0.18. Now, what that basically means is 16 to 18% of the water will be blocked by the actual netting itself, and then the rest of it should be able to pass on through. Now, the real challenge is that when you start looking at the flow regime and the forces that are acting on the net, you have two scaling processes that are incompatible with each other. Now, the first is the scaling law for Froude scaling laws. We use these to scale the waves and the dynamic of the system in that sense. But we would normally use Reynolds scaling to scale the viscosity or the drag effects that are actually happening on the net. And the net itself is actually feeling both of these two conditions. But because you can't mathematically combine the two of them, there has to be a bit of a trade-off to represent a net that covers both. What does that drag regime look like? But also, what does the wave and motion effect look like? So we ended up with a netting that was as close as we could possibly get with the materials that we actually had available. Now, to model the mooring, we simplified the mooring down to a horizontal soft mooring, and instead of modeling a catenary mooring like has been proposed, we opted to actually model something that was really basic, so we could actually understand how does this system actually move, how does it behave, and what happens when we submerge it below the surface. Now, to do that, I used a steel post, which was fixed to a structure over the top of the water. We attached a load cell, a latex spring, and then a series of mooring lines with a pulley system on the aft end of the actual model. And what this meant was we could get a really good representation of the model in its free-floating condition. And then we were able to submerge the model to the desired depth, which at full scale is about 30 meters. And we could get an apples and apples comparison. And this is really important because we want to be able to tease apart what the effect of submerging the model deep down into the water actually does do. So let's have a look. This is a regular wave. At full scale, this wave height would be about 7.5 meters in height. It has a wave period of about 12.5 seconds. And it looks nice and calm here in the video, but I assure you that it probably would not be that much fun if you were out there at sea. Now, what we can see is if you look at the forward part of the model, there's quite a large amount of turbulence as the front of the model itself goes in and out of their waves. And you can also see that the crest of the wave is actually rolling off over the top of the structure itself. And if we had 7.5 meter waves regularly rolling over the top of the structure, I imagine that would actually probably be pretty detrimental. So what we would like to do is submerge when we have these big conditions and actually see what happens. Now, if we have a look at some of the data, what I've done is analyzed all of it, and I've broken it up into two different sets. The first set is the first order responses. These are the wave by wave responses that you would actually see from each individual wave. After this, we'll talk about some of the higher order waves or higher order responses because they're really quite important. Now, all of the data that's presented has been non-dimensionalized. So wave height, the motion, in this case surge, represented by X, is non-dimensionalized by the wave height on the y-axis. And on the x-axis, the wave periods themselves have been non-dimensionalized by the wave number multiplied by the water depth. And what we can see, the surface condition, which is represented with the black dotted line, ends up with quite large or much larger surging motions than when you submerge the model below, which is represented with the red lines underneath. Now, it obviously changes for different wave periods. Typically, it's somewhere between, say, 20 and 30% of a reduction by submerging down. So that's a good thing. This is one of the important things we actually want to achieve. Now, if we look at the heave motions, these are the vertical motions as the model oscillates up and down in the waves. We start to see a much larger heaving response when the model is submerged. The motions are far more damped, particularly as we start getting to lower frequency waves. And again, this is a really good thing because those low frequency waves actually hold quite a lot of energy, and this is where a lot of the damage is done out there in the ocean. So that's two good points. And then if we look at our pitching response, we can see very clearly there is a substantial reduction in what those pitching motions actually look like across most of these wave conditions. So across the board, it's looking very positive for submerging, particularly to 30 meters. But when we come back and look at the actual measurements in the mooring tensions, we do not see as big a response or as big a reduction by submerging it. And this is really important because with a single point mooring, if we were to have some kind of failure during operation, the entire asset would be free floating out there in the ocean. So understanding what's actually happening here is critical. Now, keep in mind, these are all of the first order wave by wave responses. And if we start to look at the low frequency response, what you tend to see is that the submerged model itself in the surge direction does not offset very much at all. In fact, it typically oscillates around its original position. And this is critical because there's a clear relationship between the surging motions and the mooring tensions. And the mooring tensions also do not increase in tension as these wave periods change when it's submerged. And the reduction that you actually see in those waves is a humongous amount of energy and a whole lot of tension and force that the mooring is not actually feeling. So from a low frequency point of view, reducing and removing or submerging the model below the water surface has a considerable effect. But what about in extreme waves? Here we've got an irregular wave modeled from what you could potentially have in Storm Bay. This wave is very large. It's probably on the upper edge of what you would expect. The wave is about 16 meters and it breaks directly over the top of the model. This represents probably the worst situation you would want to have any aquaculture system in. I don't think there'd be a whole lot of the structure left at the end of it. Now, if we take that exact same wave and we submerge the model to the desired depth. And we run the wave. Here it comes. You're going to see the wave breaking directly over the top, as you saw in the previous model. And the model itself barely moves. It doesn't increase in heave. It doesn't surge backwards. It sits itself nice and in that position. And what this basically says is that submerging the model has a very large effect on the survivability of the system. And you can actually see this really clearly in this little bit of data, which is from the previous videos, particularly in surge, which is the second plot from the top, and mooring tensions, which is at the very bottom. You can see the black line surges backwards and backwards and backwards to about 200 millimeters. These are those low frequency responses which are offsetting the model backwards. Likewise, a very large increase in tension, heading towards 8 newtons at the model scale. But when it's submerged, you barely see it oscillating from the 0 point. So overall, this is very good news for the model itself, very good news for the concept, and I think it's certainly something that we should be continuing to look at the finer details about how do we actually make this thing submerge. I'd like to thank all the people in the project. It's been great working with everybody, and I'd like to hand it back to Yunil so you can introduce the next presenter. Thank you.
Thank you, Eric. Please welcome our second presentation, Global Performance of a Novel Offshore Pitch Pen in Wave and Current, a large-scale experiment study, presented by Dr. Rin Kyun Yu from TCOMS. Kyun Yu?
Yeah, thank you, Yunil, for the introduction, and also thanks, Eric, for introducing the SeaFisher project in your presentation. Let me share my slides now. Are you able to see my slides?
Yes, can you make a
okay,
full
yeah.
screen?
Yep, so I will go straight into the presentation sorry, Okay, so I'll go straight into the presentation of the model test in TCOMS Ocean Basin. I'm Ken Yu from TCOMS, and this test is a continuation of the earlier project mentioned by Eric, the 1 to 50 scale model test in AMC. It's actually a very great experiment, and we are continuing it into a 1 to 25 scale test in the TCOMS Ocean Basin facility. The objective is to assess the global motions, the hydrodynamic responses, the wave alone, as well as the wave current interaction of the system with the SeaFisher under both normal operating condition where the SeaFisher is close to the surface, as well as in a submerged condition during the extreme storm scenarios. And then the experimental results will be useful for calibration as well as validation of numerical models developed by UQ. So here's an overview of the model dimensions. So at the 1 to 25 scale, the model length is about 4.8 meter. The width is 1.6 meter, and the depth is 0.8 meter. The model is fabricated with a few different type of materials. The main frame is made of HDPE pipes with an outer diameter of 40 mm. And the top and bottom pyramidal structures, we use aluminum pipes to construct them with an outer diameter of about 6 mm. The frontal plate, as you can see here, the pink color section in front, which in the prototype is actually used to prevent floating objects from colliding with the SeaFisher. So we construct this using ABS plate with a thickness of 3 mm, and they are actually supported by HDPE pipes to strengthen it. And the whole SeaFisher model also consists also have a diagrid system. Basically, it's a stiffener system made of HGFRB rods to further strengthen the structure. For the nets, I think Eric earlier introduced, we are modeling against based on the prototype Kiko net with a solidity ratio of about 0.16 to 0.18. And for the experiment, we are using a polyester net, and we try to match the solidity ratio as close as possible. So we have a net of roughly 0.14 in solidity ratio. So for the ballast system, we have two different ballast mechanism. The fixed ballast, we are basically using a steel bar, inserting it into the HDPE pipe. So this, because, and then of course we also have foam. to secure it in place. This is a fixed ballast because we have to do it during the fabrication stage, meaning to say that once the steel bar is inside, we can't easily remove them. And we use this to achieve the desired mass for the operating condition, okay, which forms the inner ballast of design of the SeaFisher. But of course, when it comes to the submerged condition, we will need additional mass. And for that scenario, we are using a flexible ballast system. Basically, it's a steel clamp that we can easily attach to the horizontal and vertical pipes of the SeaFisher in order to give us the extra weight to submerge the model. But when we don't need it, we can easily detach them as well and bring the model back to the surface conditions. So the SeaFisher is based on a single point mooring system and is actually modeled in this 1:25 scale experiment. We have all the mooring components shown here, and the blue color sphere here is actually the central buoy that's used to hold the mooring lines. And before we start the experiments, we have also checked the mooring line stiffness between the design as well as the measured value, and it shows that we are able to achieve stiffness that is comparable to our design value. So this is the as-built photographs of the SeaFisher. So all the pipes, right, we actually have end cap to seal them. The advantage is that if in the event there's any water ingress in any single element, it will be contained within the element and we can easily rectify them. All the pipes are connected using a 3D printed joints, okay, in order to hold all of them in place. And the diagrams as far as the nets, they are secured to the HDP pipes using a special custom-made clamp that is attached directly to the HDP pipes. So this is a overview of the ocean basin facility that we subsequently transfer the model in to do the test. The dimensions is 60 meter in length, 48 meter in width, and 12 meter in depth. So the wave generation can be from one side, which is currently shown on the video. This is what we call the primary wave direction. But we also generate waves from the perpendicular side in order to give us a 45-degree wave, incident waves. And this is useful because it allows us to generate not just wave alone, but also wave current interaction with the SeaFisher model. And this is the towing carriage that we use to mount our instruments. And the SeaFisher position is actually roughly close to the middle of the basin, which is just after the carriage. So a sketch of the design. So the SeaFisher model is close to the center of the basin. We have our Qualisys motion tracking system mounted on the carriage to measure the six-dot motion of the SeaFisher. We also have rooftop video cameras as well as underwater cameras to obtain photographs and videos of the SeaFisher when it's subject to waves and currents, as well as other scenarios. The wave paddles are on two sides, so that allows us to generate collinear wave current interaction with the SeaFisher model, as well as oblique wave current interaction, which is at 45 degrees. So on the right side is a photograph of the SeaFisher from the ceiling, from the rooftop. So the surface condition, and if you notice the bottom submerged conditions, there are a few yellow spheres. Those are depth control buoy, meaning to say once we add the additional ballast, the model will actually sink, but we need to hold it at about 1 meter model scale below the free surface. So this is achieved by having the depth control buoy to hold it at that particular elevation. And from the side view, the surface condition, where you can see that the model is slightly emerged from the water surface, but for the submerged condition, they are located about 1 meter below the free surface, which translate into about 25 to 30 meters at prototype scale. And for the test conditions, we have done white noise cases, regular wave cases where we have a wave height of 2.5 meter to 7.5 meter prototype scale. Of course, everything is reduced by 25 times at model scale. We also have irregular wave and current interacting with the model. So in this case, we have 5.0 meter HS and 7.5 meter HS. And TP is 10 seconds and 12.3 seconds. In fact, the last case is one of the most extreme scenarios. We also have a current. They are uniform. We only have uniform current in this case. 0.8 meter per second over the entire water depth. So what we are showing here is mainly for the heading of 0 degrees, but there are also test cases involving the oblique wave current interaction, which we will share in future publications. So for the submerged conditions, similarly, we also have white noise, regular wave cases, as well as irregular wave and current interaction with the model. And on the right side is the properties of the model for submerged as well as surface configurations. Okay, so for the surface condition, we noticed that the RIO was slightly lower for regular wave cases with amplitude that's larger than those used in a white noise condition. And this could be due to additional damping from the structural components that's above the free surface. Whereas for the submerged condition, the heave and pitch RIO derived from the regular waves noticeably lower than those from the white noise. And this is could be attributed to damping induced by the depth control buoys that are absent in the surface condition. But in summary, for the surface versus the submerged condition, we noted that the first order surge response is significantly lower in the submerged configuration. Okay, and here are some videos of the model when they are subjected to waves and currents. This is the extreme case, HS of 7.5 meter, DP of 12.3 seconds. So the video on the left side is the surface scenario, when the model is just slightly above the free surface, the top of the model. And then the right side is for the submerged condition, where the model is below the free surface, but you will notice that there's the depth control buoys that are floating on the surface. So we can see that due to wave action, actually the model has smaller response when it's actually submerged below water, and this is below the free surface. And this is important because it's one of the design objectives is to minimize the motion to the model, to the prototype when it's under extreme conditions. So for the model at surface, the SeaFisher actually experiences much larger motion and higher hostile tension in extreme seas compared to operating seas. So this is something expected because the extreme scenario has much higher HS as well as TP. Then these are some observation on when you actually bring the model down. Okay, so initially when the model is at the surface, which is indicated by the red line, you can see that this is actually the measured surge motion as well as the hostile tension. But when we bring the model down to prototype is 30 meters below the free surface, we noted that the surge actually is reduced by almost 75%, and the hostile tension is reduced by approximately 80%. So the advantage is that it's actually helped to reduce the motion on the SeaFisher when there's an extreme storm approaching the fish farm. But at the same time, we notice the same pattern for the heave and the pitch motion. That means the submerged condition actually will actually give a smaller heave and pitch motions at the wave frequency. But there's also an interesting observation here is that when we look at very low frequency, apparently the submerged condition has an increase in energy at very extremely low frequency here. So you can see indicated by the blue arrow. So this suggests that the depth control buoy itself may actually contribute some low frequency motion to the setup, even though at the wave frequency, most of them are actually behaving as expected. When we bring the model down, we deeper into the water, we actually see less motion, but somehow the low frequency component is higher for submerged condition, and we think that the depth control buoy could be one of the key reasons, but this will be subject to further investigation in future studies to look at why the buoy is contributing to this behavior and how we can address that. So in summary, so we have conducted a large-scale experiments with surface and submerged conditions, and also with wave alone, as well as combined wave and current flows interaction with the SeaFisher. And for this study, we actually carry out a single point mooring setup, meaning the model is only attached with a single mooring spring line, and that allows the model to also weather wind when subject to the flow conditions. We also noted from this study that the nonlinear effects such as damping should be the wave height dependent damping should be included, as this could be caused by the surface structural components that is above the free surface, as well as the effect of the depth control buoys on the model and the prototype. But clearly from the test, we see that submerging the SeaFisher actually has definitely a clear advantage under extreme sea states, as it helps to reduce the surge motions as well as the hostile tensions. And this will help also to minimize the risk of structural overstressing as well as the failure of the mooring line. So what is the impact? Basically, this study as well as the work that's presented by other speakers in this webinar will actually help to support safer and sustainable offshore aquaculture designs and help to contribute to a better understanding of the dynamic behavior of the submersible fish pen systems. So with that, that's the end of my presentation. Yeah, thank you.
Thank you, Qianyu. Next, it is our third presentation about beyond the pipelines, experimental testing and constitutive modeling of HDPE for offshore structural applications, presented by Professor Hassan Krampal from Griffith University. Hi, Hassan.
Hi, Unil. Thank you very much. Also, thank you, Eric, and other team members about talking about the SeaFisher design. So I'm Hassan Karampur. I'm a structural engineer based at Griffith University in Queensland, Australia. I have been involved from the very early days in the design and testing of the SeaFisher. We do have a big team working with us. So at Griffith University, York, Ian, Lazarus, and Martin have been working hardly on this project, as well as the UQ team. We've been working with CM and yourself, Unil. Also very lucky to have a manufacturer local to us, Fusion Australia. Ethan, Max, and other team members have been really great team players, helping us to actually build manufacturing and as well as testing and some consultation around the testing of these materials. And finally, like a very kick on it, Hugo has been very experimental and helpful with these projects. So the tests that we have done are half scale. So as the first presentation explained what the SeaFisher looks like, pipelines in 4 assemblies made of HDPE with 20 meters in length and also connected together with connectors, which are quite big structural connectors. So first days of this project, again, with my background in oil and gas, we were all thinking about steel structures, offshore jackets, platforms. And the first thing comes to mind is making something which is quite heavy and strong, which is made of steel. But after that, talking to Tassel and Ewan, and also getting an opportunity to see the operations next to Hobart, we understood that HDPE is a great material. So that was my first experience working with HDPE in this project about 5 years ago. So the design philosophy changed. So the beauty of HDPE is it's corrosion resistant, it's lightweight, it's also flexible. It's a very forgiving material. You bend it, you come back the day after, and you see a lot of that deformation has been already resolved, going back to straight. On the other hand, the material is a bit different. It's not a construction material like steel and concrete, which has been around for quite a while. It's non-linear. It's from very early stages of loading. It's viscoelastic, but other benefits, I think, make it a very good choice for the SeaFisher design. So we decided to go ahead half a scale. That means the diameters of the SeaFisher part, which is 500 millimeter, we went down to 250 millimeter. What we didn't change is something which is called SDR. That's a standard diameter ratio. So that's the outside diameter divided by the thickness. So the 4-pipe assembly has a wall thickness around 23 millimeters. The organizers, which are used to centralize these 4 parts, they are 315 millimeters, same SDR, so about wall thickness of 29 millimeters. To put these parts together to get a 20-meter length, we need to do butt fusion welding. Not required in this project. We got them in 6 meters, which is with the restrictions that we have in our lab, the length that we wanted them to be. I also have to mention that a lot of these pipes in larger diameter come from a big supplier based in Europe called Agro. and they have done a lot of these floating structures around the world. We also need extrusion welding, which had been done by Fusion guys, and extrusion welding is required for the connector sections. The connectors half a scale are 1 meter in diameter and a higher SDR, which means a lower thickness compared to SDR 11. But again, the thickness that we have for the pipe is about 59 millimeters. The thickness of top and bottom plates are about 30 millimeters. So quite chunky materials, if that makes sense. At some stage during phase 2 of this project, we were advised by Bureau Veritas through an approval in principle that we need to do some feasibility tests, especially to make sure these connectors can take the required loads that we think they should take in the full model in terms of punching shear and beam shear. So that was the main philosophy behind designing these tests. Just quickly going through, if you don't have that HTP background about welding, butt welding has been around for quite a while. HTP pipelines are very well regulated. You probably have seen them in infrastructure. They can carry water, but also gas. They take very high internal pressures. So to put two pieces together, what you do, you have the setup that you can see there. You've got plates and pressure. You heat the pipes, put them together, let the fusion do the work. And then after that, you cool it down. So there is a bit of work around getting these temperature, pressure, and cooling times sorted out. But when you think of extrusion welding, you normally use a gun to weld this. And this is what we did for a lot of the connections that you can see in the design of the connector. So there's a bit of surface preparation at normally a bit higher temperature than the final welding. So about 285 degrees preheat, then use the gun to fill in the filler material, which is HTP again at a little bit lower pressure, 235 degrees. And then you apply pressure, and then of course you need to cool and solidify. Then we started doing material testing. Material testing, we followed the ASTM, American Society for Testing Materials, very well documented for plastics, rigid plastics in tensile and flexure. So tensile test, we had the part, we cut CNC cut, machine cut some dog bone shapes for tensile test from around the circumference of the pipeline, but also from different locations around the wall thickness. We did the flexure test on a single sheet. For the compression test, we decided to test the full pipe with the full diameter 250 millimeters with a length to diameter ratio over 2 to avoid column buckling. Left top, what you see is comparison between the true stress strain from all of these tests. And that was very important for us because we wanted to understand whether the material behaves kind of similarly in bending, in tension and compression, which it does to a great extent. On the right-hand side, the two figures you see is the effective strain rate or load rating, which is very important in those energetic water environments. And this is how fast you apply the load on HDPE. Unlike steel, HDPE doesn't have a clear yielding, but if you look at the top peak values here, it's between 21, 22 MPa to 25 MPa as a true stress, which agrees very well with what suppliers such as Agro claim in their catalogs. And the yield strain is pretty high. It could vary, as you can see in the table, from 7% in compression up to 10% in tension. So we are working with a material which can take a lot of strains. The other important characteristic of HDPE is the stress relaxation. So what we did is we used the same dog bone material we did for tensile testing. We stretched it to 3% strain, 5% strain, and 7%. Again, that 7% comes from previous slide, which is still below yielding. And then we maintain the strain and we measure the load drop. This is called relaxation. And we got 3 different graphs for each strain level, which again agrees well with literature. But again, bear in mind that literature had been done for other applications on thinner HTP pipes. Then we did some FEA. The FEA takes this and inputs it as a material time-dependent behavior, something known as the Prony series formulation. Then we tested the compression test and also the bending. Well, I'm not showing the bending here. And our FEA model, the computer simulation, managed to give us a very good prediction of what we actually later saw in the cyclic testing in compression. So we have these properties which then can be used for future FEA investigation with relatively good confidence. Next test was to understand how these parts bend. So bending comes from all of the environmental loads as well as the self-weight of the net, also included biofouling in future. What we wanted to learn here was the load transfer mechanism between these top and bottom rows of pipes. Again, this is 6 meters in length. The actual SeaFisher is 20 meters in length. We do a test which is known as 4-point bending test, and it's a normalized non-dimensional test. So whatever happens in this bending region, measure through all of these instrumentations in terms of deformation, strains, and also curvature and bending moment can be later extrapolated to different lengths. We also needed to benchmark against the single pipe to see what is the difference in performance. A couple of videos here. I need to probably fast forward, but what we did in either test, we started pushing down the pipes to produce some sort of bending, and then we went up one cycle, let it relax a little bit, do another cycle. So the reason was to understand that stress relaxation effect, which I just talked about in bending of these pipes. So probably a quick fast forward will give you an idea of what is happening here. Of course, the single pipe can take a fair bit more curvature compared to that mechanism, but definitely prove the feasibility of the test. Then looking at the results, we found a few interesting outputs. So the first one is the top and bottom pipes show different curvature, and that's because of the load transfer mechanism, which is through the organizers or those bundles that were welded around these pipes. All of the strains remain within 3 to 4%. I mean, below 3% mostly, which is where we want to be in terms of a compliant design for HDPE. So again, with a very good factor of safety below yield capacity. And also, very interestingly, we found that the moment capacity of the 4-pipe assembly is more than 5 times of the single pipe. And of course, the load relaxation that happened after 10 minutes wasn't more than 30%, which is another important parameter to include in the design. Next one was the test of the connectors. As you can see, in the design of the connectors, we always had the end in mind. We wanted to have modular construction, so the stems are all welded to the main body of the connector, which is again another huge circular round pipe. And then at the ends, we have stainless steel flanges and also stainless steel MC16 bolts. So the pipes can easily be bolted onto these stems for modular construction. So the first test we had to do was the punching test. In the punching test, we had a huge steel plate on top trying to punch this down. Most important for us was to understand what is the kind of load deflection behavior, whether there is any post-failure reserve in the material, and most importantly, what is the failure mode. So the things we realized, we did the monotonic test. We put about 40 tons on it, no failure. We went to 35 tons and started doing cycles. Again, no failure. It gave us a bit of confidence. Now we're brave, going 10 load cycles at 50 tons. And that's where we observed some sort of failure. And that failure only happened in the interface where we had these triangular stiffeners. So again, a fast forward, you see how it goes up and down in the cycles. And we always produce a hysteresis because we learn a lot from this graph in terms of energy dissipation. Next figure is the full load, which is the 50 tons. And now if you look, you probably see some sort of failure here. Again, very, very difficult to observe, but this is something I have a better picture of in future. So after we finished the test, we took the sample out, cut it. We were interested to see where the failure has happened. The weld itself doesn't fail as you expect. The weld is as strong as the parent material. There was interface failure, as you can see in the photo. So this is something definitely can be improved in future, but shows again a good idea of the feasibility. The final test on the connector was the shear test. In the shear test, we couldn't do cyclic, we just did monotonic. This shows a bit of the scale, and the videos, I think they are kind of self-explanatory. If you keep an eye on the stiffener on the bottom here, as well as the one that you see there, you gradually see some sort of failure at very, very high rotations. In all of the designs so far, we have accounted for the connectors to be as rigid as possible, and I think this is a testament. So it goes back to all of those towing tank tests, and it kind of proves the concept that the connectors can be very rigid. Don't want to go through a lot of these data, but again, even strains at the high failures were about 4 or 5%. So if you have a background welding steel, you know nothing over 1% is ever acceptable. But what we see here is much higher strains. Again, load relaxation, very similar to bending, if you remember, is about 25 to 30%. And finally, a few slides of the net testing. As I mentioned, we used the Kikonet, which was supplied by McAfee from Malaysia. Kikonet is orthotropic in response, which means in the longitudinal direction, it's stronger than the transverse directions. We had 3 types of tests. One was to understand its strength, in tension in the longitudinal, in the transverse, and also out of plane. Out of plane is mainly to understand the effect of any attacks by seals or any other predators. We maintained a uniform dimension of 1 meter by meter in all of the tests, so that would make our lives much easier to interpret these results when we scale up. So first test on the left-hand side is in longitudinal direction. A meter takes about 50 kilonewtons, so like 5 tons before it fails, but look at the displacement, about 50% strain. In transverse direction, there is a bit of softening, which is different as to what you can see in the longitudinal direction, but that initial softening doesn't happen until about 30% of strain, but lower capacity, like 1/4 of the other direction. Out of plane, we measure stiffness at different locations, so about more than 1 ton over 1 meter. But what was interesting is we tried to understand what happens if the net is not perfect. So in the middle, we took about 40 strands, and we abraded about 50% of the each of these monofills cross section, and we saw a significant reduction in capacity by 72%. So that has to be accounted in the design. We also did cyclic testing. Again, the whole idea is producing some hysteresis and also understand what is the nonlinear behavior, because in future modeling of SeaFisher, everything pretty much can be modeled nonlinear in the hydroelastic design. So I just want to finish. I probably went over a few minutes. So most important findings are mentioned here, but what I want to say is we showed feasibility of the design. We know that we can scale up. We know that we can have a modular construction, and we have results now that then can accurately be used in software simulations to accurately predict the behavior of the SeaFisher if required for different operational situations. The design can also be optimized. So more than happy to be involved in Q&A later or answer any questions. Thank you very much.
Thank you, Hassan. Our fourth presentation is about automated ballasting system designed for offshore submersible fish pen SeaFisher, presented by Ryu Jianyu from National University of Singapore. Jian.
Hello, Union. Okay,
Yep.
thank you for introducing. I will share my slides. Okay. Please keep in. I need to switch the. No. Okay, sure. Okay, I think everyone can see my screen. Okay, so
oh yeah, now we can see you.
Yeah,
Go
okay,
ahead.
sure. So, okay, good afternoon, everyone. My name is Zhi Yuan, from National University of Singapore. So, this afternoon I'm going to show my work for the SeaFisher projects with regard to the automated ballasting system design. So let me firstly introduce the motivation behind this work. So because the offshore aquaculture is becoming more and more important due to the shortage of the neutral species and some of the potential challenges induced by the environmental challenges, for example, the critical storms or the harsh marine conditions. And in phase one of this project, we propose the practical solutions to submerge the entire fish cage to below the water surface level to a relatively depth level to eliminate the potential environment impacts on both the fish cages and also ensure the well-being of the farmed fishes. However, the reliable submergence and floating process need a effective blasting system, and also the manual operation in offshore operation environments may not be very time efficient. So in this case, we developed a automated blasting system under the digital twin framework to ensure efficient and timely responses to these offshore fish farming demands. So as you can see, this is the overall digital twin-based automated blasting system, and it's actually to create a closed loop communication between the physical assets together with its digital representations, and it actually covers the entire surface life of the fish cage systems, including the normal operation, critical storms, and the maintenance and annual cleaning scenario. So we may firstly start with normal operations. So in the normal operation, the SeaFisher cage normally stand in a standby mode, just stay at the water surface, but it's continuously collecting the environment data, for example, the whip height and wind speed to the system, and comparison against the predefined threshold values to detect whether the critical storm is coming or not. So once the threshold is violated, and the system will automatically trigger the submergence commands, and the entire normal operation status will be converted to the critical storm status. And during this process, we need to release the compressed air within the blasting tube, and during the entire submerged process, we need to regulate the air release rate together with the depth control buoys to ensure a safe and stable submergence until the entire fish cage arrive at target submerged steps. Okay, so after that, we need to wait for the critical storm passing through, and the floating commands will be activated through the re-injection of the compressed air to let the entire fish cage back to the water surface and remain at the standby mode for the normal operations. There are also two special scenarios we need to consider. One is about annual cleaning. In this scenario, we need to use the inflatable airbags arranged at the bottom of the fish cage to lift the entire fish cage up above the water surface, so the exposed net surface could be cleaned in this period. And for the maintenance, the system should shut down, waiting for the potential diagnosis, inspections, and repairs by the operators, and the backup powers will ensure its reliability in this period as well. So beside these three working scenarios, it actually also needs three integrated hardware layers to ensure this kind of different operation demands. So the core of this hardware layer is the sensor-based automated control system. It's actually serve as the brain to receive the in-situ data and also do the command station and the potential communication between the open bottom blasting system and the compressed air delivery systems. For each subsystems, it actually have its respective physical equipment and implementation methods. So we firstly look at the open bottom blasting system. So for the bottom blasting systems, we actually, just like the name, we choose the open bottom blasting tube. So compare with the previous submersible fish pen designs, this open bottom blasting tube is relatively simple and easy to operate because we actually rely on the compressed air volume remain within the blasting tube to adjust the overall contribution, buoyancy contribution of the blasting air, and compare with the closed bottom designs, it actually could reduce some kind of the mechanical complexity and also lower the maintenance risks as well, and also reduce more arrangements about the valves for the blasting tubes. And as I can see, we actually have two important process, submergence process and reflowing process. So let's take a look at the submergence process, for example. So once we actually activate the submergence commands, the compressed air will be vent out of the blasting tube, and then the buoyancy contribution from the blasting air will decrease, and this will drive the entire fish cage further submerge below the water surface. So this is the phase one of the submergence, and at the end of this phase, the entire fish cage already fully immersed under the water level. So any compressed air venting or the compressed air buoyancy contribution decrease, it will trigger a relatively negative buoyancy. This will drive the entire system begin to submerge to the target depths. And in this process, we need to carefully deal with the compressed air venting rate together with the depth control buoys reactivation to ensure a safe and stable submergence. So the refloating process is just like the reversed version of this submergence process. Is actually re-inject the compressed air to generate a controlled positive buoyancy and to drive the entire fish cage back to the seawater surface. So as I've mentioned, the depth control buoy actually in this process play a very important role. It provides supplementary buoyancy to help the entire submergence and refloating systems in a stable state. And in the general layout, we actually sit both primary and secondary buoys to provide stage buoyancy support through these extensible codes. These different extensible lengths can help us to adjust the buoyancy contribution at different stage of submergence or refloating process, and also provide redundant buoyancy if any unexpected failure of some certain buoys. And also we need to consider the entanglement risks between the two adjacent buoys. So we consider the most unfavorable scenario for ensure the entanglement angles could reach into 40 to 50 degrees, and this could be acceptable by considering the low frequency oscillation in the offshore environments. And then as to the compressed air delivery system, we actually need to consider how to control the air out or into the system, and also how the delivery air is delivered to the specific blasting tubes. So this is the overall architecture of the valving system design. So it's actually have a main control valve to control whether the delivery air should be transferred or delivered or not, and also two series of the motor valves sit as the top of the blasting tubes and the delivery hoses to regulate the air venting or air injection during the refloating and the submergence process respectively, together with some fine control to one specific blasting tube together with the bubble tubing technique. We can use it to do some local trim and inclination control. So this is the illustration of the bubble tubing technique. They actually use very fine voice distributed along the delivery hoses, and to distribute fine bubbles. This will help reduce the local jet impacts and any cavitation related erosion risk to the inner surface of the blasting tubes. And also we use some preliminary calculation to show its capacity in the delivery of the stable compressed air. Then we need to consider the most important automated control system. It actually integrates full sensors on site. For example, the wind speed sensor, the wave height sensors, the water pressure gauges to monitor the submergence speed and depth respectively, together with the inclination angle monitor and the GPS locating sensors. And all of data will be fed into the digital twin, and then it will do some possible analysis and the digital representation to give out the reliable commands for each subsystem to control whether the air should be injected or not, or the depth control point should activate or not. So the digital representation of submergence process, we actually just to describe the main submergence process from the water surface to the target tips at 30 meters below the water surface, and it considers the residual air buoyancy contribution together with depth control buoy support and the hydrodynamic stress in the entire submergence process, with three design logic. One is the normal submergence, another is the deceleration, and the possible holding to avoid any destabilization during the submergence. And through the numerical results, we can basically to see it's have the capability to provide a safe and stable submergence control within the 4 hours period. And as to the refloating process, it's the main challenge is actually to describe or deal with any compressed air volume expansion during the refloating process, because the drawing process will have the different or varied seawater pressure change and will trigger the excessive buoyancy contribution from the ballasting air. So we also need to consider the compressed air venting, reinjection, depth control buoy activation together with the hydrodynamic stress forces. And using the switching between the venting and the injection, we can just use the simulation result to say, okay, it can provide a good refloating control within the user-defined speed threshold, and the overall time period is within 8 hours. And then we just use a case study to validate our digital twin-based framework. And this submersible fish cage system is actually designed by the previous Korean researchers in 2011. Although it is a closed bottom blasting tanks, but it's shared similar principles to use the compressed air to control overall submergence and refloating process. So we just use our numerical re-encapsulate numerical model to calculate its depth versus time response, and do the comparison with its numerical and environment data to show relatively good agreement between these two results, and to preliminarily support our SeaFisher data framework in this study. And so in summary, actually, we just proposed the digital twin-based automated blasting system, and to integrate the institute sensor data together with the compressed air injection or the venting schemes together, and also the depth control buoy activation or deactivations to ensure a safe and effective offshore fish farming operations. So I think that's all for the automated blasting system design. So I'm looking forward to your questions. Thank you.
Thank you, Ji-Won. Okay, we proceed the next presenter. Please welcome our final speaker for this webinar, Dr. Jod Wigerink from BMT, whose presentation title is Functional SeaFisher, Configuring Feed, Air, and Power Delivery Systems. Hi, Jod.
Thank you, Neil. Give me 1 sec to, yep. All right, thank you for the introduction, Neil, and the opportunity to speak here. I'm a marine structures engineer with VMT, and as part of the scope with the novel fish pen design project, it was to create a functional fish farm and include functional and operational criteria into the design. In this presentation, I want to take you through some of the considerations that require further development for the SeaFisher to functionally operate in a next stage. Yep. Yeah, so the current project has been very heavy on the structural design and the hydrodynamic behavior. And as we move forward out of a more research phase and look towards more a development, like into a deployment, we really need to divert our focus to work also on things that actually functionally facilitate the SeaFisher to operate, and where we can look at or end up with a product where we've got fish in the fish pen that are happy and grow well. Yeah, so that's part of the focus that I want to talk about today. So when we talk about SeaFisher, we typically only look at the structure where the fish reside. But if we look at the whole fish farm, there's more to it. So we've got a feed barge and a umbilical to provide the functions that the SeaFisher needs to operate. And as part of as part of the feed barge, there's a power control system with a power backup facility. There's a wet feeding system so that we can also feed the fish when the SeaFisher is submerged. And there's two air systems, one that we just talked about, the buoyancy control system, and there's also one for diffusers that will be suspended below each fish pen, which will create an upwelling flow through the fish pens to in low energy states, and if there's inefficient oxygen in the water column, and then we can still provide fresh water to the fish. And all these functions, which include electrical interfaces, pneumatic or air interfaces, and the feed pipes, that will be integrated into the umbilical to be routed to SeaFisher. So for the SeaFisher to successfully operate, the mooring system is a critical component. And there's two flavors in mooring the feed barge in combination with the SeaFisher. We would either like to moor it in front of the SeaFisher or moor it behind the SeaFisher. But when mooring it behind SeaFisher, effectively SeaFisher becomes part of the load-bearing structure or part of the mooring system, and should be able to withstand the loads that the large surface waves in survival conditions exert on the feed barge, which at this point it's not designed for. An interesting finding from the experimental investigation was that the SeaFisher itself is quite sensitive to pitch. So imagine having the SeaFisher submerged, and we've got a feed barge that cops all the environmental loading. There's a high risk of distorting that vertical equilibrium that keeps the SeaFisher below, and we don't want that. So there's a preference for the feed barge to be moored in front of the SeaFisher. However, that also comes with a challenge, because we've got that single point mooring system, and the feed barge mooring system will have to branch off that one way or the other, where you probably end up with some form of triangular mooring arrangement with an umbilical that also intertwines with that, and that can become quite complex and prone to tangles, and that's what we absolutely not want. As part of the investigations, we did some preliminary modeling with the feed barge to develop develop insight really to see how the feed barge would behave. And as part of that investigation, we change the mooring line stiffness. And if you increase the mooring line stiffness, you effectively reduce the footprint in which the feed barge would move in the horizontal plane. However, with large waves, you pretty much drag the feed barge through the waves rather than sailing over the waves. And if you reduce the stiffness, you very much increase the footprint, and the feed barge just goes on a walk. Also in an out of control fashion at times. So there's a horizontal constraint there that we need to consider in future potential experimental setups. And another constraint is the length of the umbilical. So let's say we're farming in a water depth of 100 meters. That only if we've got an umbilical of 200 meters, there's a chance that at some point it might hit the seabed, and we don't want that. So that's another constraint that we need to consider to prevent any snags or damage to the umbilical, as well as overstretching or the radius of the umbilical becoming too tight and kinking and damaging any delivery of the functions to SeaFisher. So in conventional fish farm configurations, you typically see that you've got the feed barge and you've got individual feed pipes running to each of the individual fish pens. And when needed, they can get bundled to prevent any damage. But if one feed pipe would fail or damage, then typically these get replaced as a single feed pipe. But with SeaFisher, that's going to be different. So all the feed pipes are going to be bundled into an umbilical bundle. And then when it interfaces with SeaFisher, there's a much more permanent setup where it gets routed to the individual fish pens and to the fine, like for the air delivery system, it's going to be to the buoyancy control tanks. There has been a study with the Blue Economy to look at the best way of bundling these pipes. The suitability for SeaFisher is not definite. It is very prone to biofouling, and ultimately, what you want to do if you look at commissioning the fish farm, so you first install your single point mooring system, then we install the SeaFisher, then we install the feed barge. You basically want to do a quick connect, which needs to be designed. And if you get damage to one of the pipes in the umbilical, operators should be able to go into the fish farm with their maintenance equipment, undo the whole umbilical as a whole, and reinstall a whole umbilical rather than replacing single pipes in the umbilical. There's other applications in the offshore industry where you integrate multiple functions in a single umbilical. It comes with a cost because they're not cheap. But there are ways to reduce the complexity of reduce that bundling component and the proneness to biofouling. So just to wrap it up here, there's a few things that are critical for moving forward, and that's that we should start investigating. We should put more focus on the interaction between SeaFisher and the feed barge, and with the feed barge, there's the hull forms that play a role, the dynamic behavior, and the design, how we're going to configure a feed barge in a high energy environment. But then that ties into the mooring arrangement and the dynamic coupling between SeaFisher, which has got a completely different behavior than the feed barge, and you've got the constraints there. So that becomes quite an integrated and really interesting problem to solve. But it will require some strong focus moving forward, as well as the umbilical connections. We need to get that right. Otherwise, there's no way we're going to put fish in there. And then with that, I want to wrap it up and hand back to you, Neil. So thank you.
Thank you very much, Jod. I will now facilitate a Q&A session for the remaining time available. So far we have a couple of questions. I will read one for you. For the presenter, can you make your video on so that everyone can see your face? Yeah, thank you. So first question is, thank you all for the information. As a non-technical physicist, one of the difference between steel and concrete structure is that it doesn't float. With the decision to proceed with HDPE, how do you get it to submerge? Also, was there any inclusion of interior baffles used in the piping? If no baffles, what has been considered for breakage or repair of damaged sections? Hassan, can you answer this question?
Probably I can answer the second part of the question, the
Yes.
submerging and ballast. I think there was a presentation around it. So baffling is a very good point actually. So we have designed it modular. So if there is any local damage, we don't need to undo the entire structure. So the local damages can be repaired locally. That was the main idea behind the design.
Okay. Thank you, Hassan. Probably I can give a little bit answer about the first question. So the design for SeaFisher, we deliberately include filling material inside HDPE. So for example, bottom frames, we use sand to make it heavy. And also we have a ballasting system that can capture some additional mass from the seawater. So that was capable to make the SeaFisher submerged. I think it's good enough for the answer. Do you guys have any further question answer for this question? Okay. And then I will look at the second question. So what consideration have been given to long-term effect on the key cornet? For example, fatigue, degradation due to sun exposure, degradation due to seawater exposure, and do you have any assessment of lifetime of the key cornet before it needs to be replaced? I think it's relevant to the net testing, but
Yeah, kind of. So
kind of, but we
we're
are
very
not.
cautious about commenting on a commercial
Yeah.
product, but I've heard from industry there seems to be a bit of confidence in using Kikonet for those environments, especially with being UV kind of resistance. But the question around fatigue is very relevant, and it's part of the research that we're doing. I may have skimmed through my slides very quickly, but we have done some cyclic testing of the nets in both directions. So again, to have a good understanding of fatigue, you probably have to do more than 100,000 cycles to get a proper SNN curve. But what we need to understand at the moment is for each operational or floating or submerged conditions, how many cycles produce strain, which is still within what we call a compliant design. And that's what we're trying to predict from our limited tests, but it can go into our simulations.
Okay. Thank you, Hassan. Next question is, does the SeaFisher have 12 partitions? Let's say 12 separate pens. Does the salmon industry partners have any thoughts or comments on the size of those individual pen units? I think it's more like an operational aspect. We did some very beginning. We had a conversation with our industry partner, Tasai and Huon, but obviously the size of 12 units is not big enough, but it's targeting the biggest size of conventional fish pen. So we intend to utilize the multiple SeaFisher in one place to accommodate a larger scale. And also, as this is more like a modular, it's not only limited to 12 units, it can be more like 2x8 or 2x10. It depends on the environment condition in the farming site. So I just can answer this in this way. Probably it's need more consideration with the industry partners, what they need for the farming scale. Okay. So I would take more technical questions. Can I use a ballast water compare air for submerged fish cage? So we use ballast water for submerged fish cage, but the air is filled when it needs to refloat to the water surface. Yeah. And please share all presentation we share in the later, so you can download or you can watch it online. No question, just want to say great presentation from all. I think I touched on all the questions, so there is no further technical question. Thank you all. It was very nice. So thank you again to all our presenters and everyone that has joined online. The recording of this webinar will be available in the coming days. So please check out the CRC's event page for any upcoming webinars and events. So have a great day or evening from wherever you are watching from. Thank you so much.